Here we have a satellite in orbit around the Earth, and it's going to have some gravitational potential energy because of its height. But at the same time, it's also going to have to be moving at a certain velocity, because if it wasn't, it'd be pulled in by the gravitational attraction and would fall in. So it needs to be going at a certain velocity in order to circular motion around the Earth there. So it needs some kinetic energy as well. So a really useful expression to determine is the gravitational potential energy plus the kinetic energy to give the total energy. I'm going to show that the total energy of an object in orbit is given by this equation, minus gmm over 2r, capital M being the mass of the object in the center, lowercase m is the mass of the object that's doing the orbiting, and r is the distance from the center. So first, let me ensure that it's in a circular motion orbit, in a stable orbit around the planet. The gravitational force provides the centripetal force, so I'm going to use Newton's law of gravitation and make it equal to the centripetal force equation like this. Tempted to cancel out the m's, but I won't be doing that because I'm going to get half mv squared later, so I'll keep those m's there. And then I'm going to cancel out one of the r's from both sides. So if I do that, I get this equation. If there was an r squared on the right hand side, it just becomes r on the right hand side like this. Then now to get half mv squared, I'm going to have to multiply both sides by half. If I multiply both sides by half, I have the equation for kinetic energy. So that's done. Now the gravitational potential energy equation, you can just get that from your data sheet, or you can do gravitational potential, which is minus gm over r times the mass to get this equation. The total energy is going to be the sum of these two added together. But you can see the denominators aren't the same, so you can't just add them like that. So the gravitational potential energy one on the left hand side there, I'm going to multiply by 2 at the top and 2 at the bottom. Now they have the same denominators. I can add them, and you get this equation for the total energy of the satellite. In part B, I'm going to describe the change in energy when the satellite has moved into a stable orbit at a larger radius. So imagine moving into a larger radius like this. So it turns out actually needs to be going slower to stay in orbit at this larger radius. So the kinetic energy actually decreases. But of course, its height has increased, so the gravitational potential energy has to increase. So we can show this. So the equation of gravitational potential energy is this. So now the denominator, if that increases, typically the number on the other side would decrease, but because of the negative, it's actually going to increase. It becomes less negative, meaning it increases. Okay, so the gravitational energy increases as the distance from the center increases. That should make sense. That should be okay. Now the kinetic energy equation has gmm over 2r. So if r increases, then there's no negative here, so the kinetic energy will decrease. So it doesn't have to be going as fast at a larger radius. So the speed and hence the kinetic energy to stay in orbit at a larger radius is less. Finally, the total energy. So which one's going to dominate? So because of the negative sign here, if r increases, the total energy becomes less negative. So it's actually going to increase. So total energy increases as you move an object further away and put it into a stable orbit at larger radius.